Ladies and gentlemen, hi together. It's really an honor and a pleasure for me to present you the results of Work Package 15 of the promotion project. For the next hour, we will dive into the world of gas-insulated switchgear. Work Package 15, that means HVDC GIS technology demonstrator. You will now learn all about compact gas-insulated switchgear and its testing and suitability for DC, as well as exciting results about diagnostics and eco-friendly insulating gases as a possible replacement for SF6. My name is Uwe Riechert. Since 1999, I'm with ABB, now Hitachi ABB Power Grid Switzerland, and I have conducted several product development projects in the field of gas-insulated switchgear, high current systems, and ultra-high voltage substations. Today I'm responsible for development and product management of gas-insulated HVDC substations and circuit breaker and partial discharge monitoring. Since 2017 I'm allowed to lead the Work Package 15 in the promotion project. To begin with, I would like to introduce the agenda. The first part of the presentation is about the Work Package 15 itself. In the second part, I will make some basic remarks about HVDC gas-insulated switchgear and the question how to reduce the size of platforms with HVDC GIS. And in the third part, I will introduce the presentations of our work package. And finally, of course, I will give a summary. The Work Package 15 has been formed to make a substantial contribution here. To increase the technology readiness level for HVDC GIS equipment to the highest level, to develop recommendations for specifying and testing of gas-insulated HVDC systems, to develop testing requirements, procedures, and methods based on simulation analysis, real HVDC onshore and offshore experiences, and also based on the secret work. The focus of our task was to carry out a long-term tests of a full-power HVDC GIS according to developed test requirements and procedures and using developed monitoring and diagnostic methods. Furthermore, we had the following tasks: to develop monitoring and diagnostic methods for HVDC to ensure a safe operation, to evaluate performance of SF6 alternatives, and finally, we wanted to improve models and develop the understanding of failure modes. In order to best fulfill our tasks, we have divided the work package into different task groups. The task group 1 has collected all the information needed to develop specification and to derive test requirements. For this purpose, the input from other work packages was used, mainly from Work Package 1, requirements for meshed offshore grids, and Work Package 4, HVDC grid protection systems. The task group was headed by sheet transmission. The task group 2 has been working on the development of monitoring and diagnostic methods and the applicability of SF6 alternatives under the lead of the University of Delft. DNVGL and KEMA Labs were and are responsible for the long-term test, and in task group 4, valuable input for the standardization activities for HVDC GIS design, testing and application was collected and passed on to Work Package 11, harmonization towards standardization. The cooperation in Work Package 15 was characterized by a very high degree of openness, by scientific interest, great experience, and close collaboration. The group was very well composed. It includes TSOs, a test laboratory, a research institute, a consultancy, a university, and a manufacturer, namely TenneT, SSE, KEMA Labs, Supergrid Institute, DNVGL, Delft University, and Hitachi ABB Power Grids. I would like to take the opportunity to thank all project partners for the interesting and exciting time and cooperation. And you can see here some pictures of our project meetings and conferences here. Dear friends of the promotion project, Ladies and gentlemen, let me now tell you about the basics of gas-insulated HVDC systems and try to give you an answer to the question how to reduce the size of platforms with HVDC GIS.
Dimensioning of HVDC GIS requires the knowledge of electric field distributions occurring at DC voltage stress. Starting from a capacitive field distribution at the moment of energization, the electric field distribution is continuously evolving with time. This field transition depends on the surface and bulk currents in the solid insulation. It results in interface charging, mainly of the solid gas interface, and space charge accumulation in the solid insulation. This animation shows the calculated electrical field distribution of a conical insulator. Shortly after energizing with DC, the electric field distribution is determined by the permittivities. The field distribution is similar to that under AC condition. The highest field strength is occurring at the inner conductor. Under DC conditions, the electric field distribution is determined by the conduction processes in the gas and in the solid. And under load conditions with high current, the temperature in the system is increasing and a temperature gradient is arising. Since the conductivity of the solid is increasing with higher temperature, the electric field is shifted to colder region. The maximum field strength is displaced from the center of the insulator to the outer area of the insulator, close to the enclosure. Based on the research of material characterization and the use of multiphysics simulation tools, the analysis of electrical field distribution is today possible with high precision. And it's possible to design insulators optimized for HVDC. With some additional changes at interface components and with the development of special current and voltage measurement devices, it was possible to design all required components. Just as in AC power systems, the HVDC GIS technology spans a number of switchgear components as shown here. Bus ducts and high voltage DC conductors, disconnect and earthing switches, bushings and cable terminations, current and voltage sensors, and surge arresters.
Based on development and research results, as well as on service experience, the manufacturer have developed new adequate dielectric test procedures. All dielectric tests were already performed, like DC withstand voltage tests, impulse tests, superimposed impulse tests, polarity reversal tests, dielectric tests under high load and zero load conditions, partial discharge measurement at AC and DC voltage stress. Moreover, new test procedures were developed, like the insulation system test and the prototype installation long-term test. Special type test standards for gas-insulated HVDC systems are not yet available today. So CGRE Study Committee D1 has installed a working group which should give recommendations, and Promotion Work Package 15 has also prepared a specification. There was also a demand from users and regulators for a full-scale demonstration of the technology readiness level of HVDC GIS. Such a full-scale demonstration, also called prototype installation test, was specified and executed as part of the promotion project. This 1.5-year long test is now finished and verifies the overall performance of the manufacturer to produce and install HVDC GIS. More details are given in the following presentation, so stay tuned and look forward to the next presentations. In ISC, the Study Committee 17 has a new working group established. The working group 42 deals specifically with HVDC GIS. Allow me, as convener, to present this advertising part to say that we are looking for more members. If you are interested, you can contact me directly. Let me say some words about the history, because the technology is not completely new. But until now, there has been a little operating experience with gas-insulated HVDC systems. The first commercial HVDC GIS was installed in the year 2000 in Japan. The 500 kV HVDC GIS is now under operation at 250 kV. A DC busbar with superimposed DC voltage of 150 kV has been in operation since 1983 and 1987 in Sweden. From 1990 until 1995, long-term tests at BPA's test center in the US were carried out for a 500 kV HVDC GIS. And the first research is already known from 1980. Today, newly more compact generations of HVDC GIS were developed and tested in the 2010s, 2 in Europe and 1 in Japan. The new compact generation of HVDC GIS installation can be built with a much higher degree of compactness and significantly lower sensitivity to ambient factors than with air-insulated switchgear. The most obvious cost-saving potential can be found on offshore converter platforms, as shown here. Such converter stations are challenging during construction and installation. Some problems could be mitigated if the platform size could be reduced. By using HVDC GIS, the volumetric space of the switchgear installation itself can be reduced by 70 to 95%, which may result in a size reduction of 10% of the total platform. But until now, again, there has been only a little operating experience. Users intended to employ gas-insulated HVDC systems expect high reliability and long-term performance. This leads to the need for long-term tests on gas-insulated HVDC system in general. And the Work Package 15 has been formed to make here a substantial contribution to increase the technology readiness level of gas-insulated HVDC systems. While you are looking here for a picture of our public demonstration event, I would like to put you in the mood of the other presentations of our work package. By the way, in the background of this photo, you can see the HVDC GIS prototype installation test. After my overview talk, you can expect 2 presentations about the prototype installation test, one about the test performed, and another one about the tested components. Afterwards, you can look forward to 2 presentations about partial discharge monitoring techniques for HVDC GIS and alternative gases for future SF6-free HVDC GIS, with focus on PD behavior and detection. And finally, I will give a short summary. Let me also introduce the speakers of the next presentations. Nadu Belda is Innovation Engineer at KEMA Labs. His experiences in developing test methods and designing of test circuits for HVDC switchgear. He is also task leader of Work Package 5 and Work Package 10 of Promotion. Hong Hee has more than 10 years experience in testing, inspection of medium voltage and high voltage equipment, especially in high voltage AC and DC power cables and DC GIS. She works as consultant for AC and DC land and submarine power cables for DNVGL. My colleague Michael Gatsche is from Hitachi ABB Power Grids in Switzerland. He works as an R&D senior engineer for gas-insulated switchgear and has experience in HVDC GIS and circuit breaker, electric contacts, high current systems, and instrument transformers. Luis Castro Herrera and Armando Rodrigo Moore are from Delft University. Both are experienced in PD diagnostic and monitoring. Luis works as a HV lab researcher and Armando is an assistant professor, and he is also the task leader in Work Package 15 dealing with partial discharge diagnostics and monitoring. Katharina Toigo and Kong-Tan Wu are from Supergrid Institute in France. Both are experienced with DC PD measurements, with investigations about SF6 alternative gases, about dielectric characterization and electrical field simulations, and Tan is also the R&D team leader at Supergrid Institute. Summarizing from the tests, it can be expected that HVDC GIS components will have equally long lifetime as known from HVAC GIS. The prototype installation test is now finished and verifies the overall performance of a manufacturer to produce and install HVDC GIS. Using insulating gas under pressure, space requirements of a HVDC switchyard can be reduced by 70 to 95%. Concepts such as a PD localization and charge estimations were investigated and proved feasible for critical offshore installations. Performance of existing SF6 monitoring and diagnostic methods were evaluated for alternative gases in the future light of SF6-free HVDC GIS.
Thank you very much for your attention.